on us like it did before. Okay. All right. Zion, I ran a 537. That's right, a 537. See if you can beat that. He can run like 537s like 10 times in a row.
That's disgusting.
All right, so
Yeah, you can come out from like a sore day and still beat you.
So we're going to deal a little bit with multi-electron atoms, just in the context of anti-symmetry. Okay, so if you recall, the anti-symmetry requirement for fermions, which electrons are a fermion, is that the wave function has to be anti-symmetric upon the exchange of any two particles, any two fermions, okay? So the easiest way to explore this is with helium, because helium only has 2 electrons. You'll see in your homework that I've given you lithium. Here's 2 candidate wave functions for lithium. And you can see how complex those are, right? You see those? They're very complex. So helium is less complex, okay? And then if you could imagine what it would be like if we went to beryllium, right?
So I have 12. Like lithium's 3, so you have 6 of them. So it's beryllium at 4.
Well, I'll show you what happens here. Okay, so the wave function for 2 electrons is the product of 2 different wave functions. Okay, so we could say it like this: psi 1, 2 is equal to 1s alpha 1, 1s beta 2. Okay, where this is the wave function for electron 1, and this is the wave function for electron 2. So if you recall back to general chemistry where you had those like box electron configurations, what this looks like is something like this. Here's the box. This is 1s. Okay? And you have one of the electrons is an up electron, the other is a down electron. Okay? And so remember we looked at the spin functions. The alpha spin function gives you that plus 1/2 h bar for the z component of the spin operator, and the beta function gives you negative 1/2, right? And so that's where we get this whole idea of like up and down spins, okay? So in the box electron configuration, this is how you would represent this. This says electron 1 is in the 1s alpha spin function. It's in 1s orbital, and it has alpha spin. This is 1s beta, 1s orbital beta down spin for electron 2. Is this wave function antisymmetric? Let's find out. Okay. So if it is antisymmetric, then we have this test that we want to apply. Okay. This one right here. So I'm going to write down psi 1, 2, which is this, 1s alpha 1, 1s beta 2. Does this equal negative 1s alpha 2, 1s beta 1? What do you think? Is this antisymmetric? Are those equal?
Are we just supposed to say yes, or are we like deriving it somehow?
I'm just asking, are those equal?
Based on
Put a question mark here. Are they equal?
Why do you have a negative in front of the?
Because that's the anti-symmetry requirement. You're like, I have no idea if these are equal or not.
If you take the first line as like truth, I guess.
They're not equal.
Okay. Why?
Why are they not equal? Because it's, look, that doesn't equal that. I mean, is what's on the left side the same as what's on the right side?
Well, that's not the same for the first one either, but you said that's true.
What, the first one? This one?
Yeah.
No, that is true.
But they're not the same.
This is the requirement. So that means that this is not the wave function. This wave function does not satisfy the anti-symmetry requirement. This wave function does not satisfy the anti-symmetry requirement. So we must come up with another wave function to satisfy the anti-symmetry requirement. So let me offer two options. I'll call it psi plus which is equal to 1s alpha 1, 1s beta 2 plus 1s alpha 2, 1s beta 1. Okay, that's option 1. And then option 2 is psi minus, which is 1s alpha 1, 1s beta 2, minus 1s alpha 2, 1s beta 1. Are one of these anti-symmetric?
Yes.
I will give you a hint. Psi plus is not anti-symmetric.
Yeah.
Let me demonstrate why psi minus is anti-symmetric. Okay? So this is psi minus. Let's write out, and we're going to write this out right below it. We're going to write out psi minus 2, 1. So everywhere I see a 1, I'm going to replace it with a 2. And everywhere I see a 2, I'm going to replace it with a 1. Okay? Is this the negative of that? Well, if we want to test it out, let's multiply it by minus 1. There's a minus. There's a minus. This is going to turn into a plus. Are these equal?
Yes.
You see that this term right here is the same as this one. And this term right here is the same as that one. You see that? So this satisfies the anti-symmetry requirement. So if you want to write this out in like the box electron configuration, you would do it like this. It looks kind of strange. We would have electron 1 is up here, and it's down here. And electron 2 is down here and up here. This would be the actual wave function. Why don't we teach this in general chemistry? Because it's weird. Isn't it weird? It's weird.
So in general chemistry, the 1s2, is that including the alpha and the beta?
Okay, so in general chemistry, when you do 1s2, this is telling you that there are 2 electrons in the 1s orbital. So that's the electron configuration.
Okay, so why don't we ever write this superscript whenever we're working with these, like helium?
Here, these are, I left out beta here. My goodness, there's a beta right there. Y'all didn't even know. Did you write it beta? Okay, yeah.
So this is showing that for the psi minus wave function, those are anti-symmetrical, but the psi plus wave function isn't. Like if you did psi plus 2, 1, that wouldn't satisfy.
Right. If you did psi plus 2, 1, you would wind up with,
Two negatives.
you would replace 2 with 1 and 1 with 2.
The sign.
And you would wind up with psi plus 1, 2 equals psi plus 2, 1. It wouldn't be anti-symmetric. It wouldn't change the sign of the wave function when you swapped 2 of them.
You have to take into account the sign and the swap.
Yes, the swap should change the sign of the wave function. Now, there's a really easy way to write these out. I usually teach it in the second semester. It's called a determinantal wave function. You can write it out as a matrix. We don't need to do any of that. This is enough to demonstrate what I mean by anti-symmetry and what is meant by anti-symmetry. Okay. Now, in your homework, let me just go back to your homework. Question number 1 says, here are 2 candidate wave functions. Man, it's not in focus. Okay, 2 candidate wave functions. You've got these. There's 3 electrons, so it's kind of complex. One of these wave functions is valid. The other is not.
Do you have to figure out the negative sign?
So you have to figure out which one is valid and which one is not
Okay, but with
by this test right here.
that's with 2 numbers. How do you do it with 3 numbers?
You pick 2 to swap them.
How do you know if you pick the right 2?
You just pick 2.
And how
Swap
this
it.
works?
Well, for these 2, for the one that is not a valid wave function, if you pick the quote right 2, it'll be anti-symmetric, but so will the other one, right? So
you have to be
if
consistent
you
with
need
the
to
two.
you need to find out which one of these, when you swap 2 of the electrons, you do not get anti-symmetry.
Okay.
That's the game. Do you see what anti-symmetry does? That's what it does. And you're just swapping 2. So, for example, you could swap electron 1 and electron 2. Or you could swap electron 2 with electron 3. Or you could swap electron 1 with electron 3. And you just fill it in. So if you swap 2 and 3, everywhere you see a 2, you replace it with a 3. Everywhere you see a 3, you replace it with a 2, and you just go through. And you're going to find out which one of these wave functions is anti-symmetric and which one does not meet that requirement. Yeah.
So then after you flip it, then you multiply that flipped version by -1. The test is anti-symmetrical.
Yeah. When you flip it,
Then you multiply that by -1.
and it should get you back to the original wave function, right? Just like we did here. So when we multiplied it by -1, we got the original wave function.
Okay.
Is the alpha and the beta, is that what corresponds to the 1s2?
No, the alpha and the beta correspond to the spin functions. The alpha spin function and the beta spin function.
I guess that's not telling you like which electron you're looking at.
The 1 and 2 in parentheses, that tells you this is electron 1 and this is electron 2. Imagine like this. F of 1, G of 2. F is a function of 1. G is a function of 2. The F function is 1s alpha, and the G function is 1s beta. Yeah.
So like on, like for example, number 1, like these are going to be different. Like whether it's a valid wave function is different depending on whether it's a fermion or a boson. Is that right?
Yeah, so these are for electrons, yeah, fermions,
Okay.
right?
So it has to be anti-symmetric.
Yeah.
to be valid.
Yeah.
Okay.
So if electrons were bosons, which they're not, if they were, this would be the wave function right here. You would add them together, and that would be symmetric. But they're not. They're fermions, so you got to go with this one. Okay, it's good. All right. Okay, so we need to move on to molecules. And talk about molecular orbital theory.
How long is this quantum unit until the exam?
We're about to start drawing a whole bunch of pictures after this.
Or what?
Pictures. Don't you love pictures? Okay. Molecular orbital theory. So just like we've talked about atomic orbitals, s orbitals, p orbitals, all that stuff, there are corresponding molecular orbitals, which are a combination of all of those. Okay, and the simplest molecule is H2 plus. Okay, you've got a hydrogen atom here, which is a proton. A hydrogen atom here, which is another proton. And then you have some electron. Okay. And the electron and the protons are separated by some distance r. And the electron is separated from proton 1 by R. What do I have in my notes? RA? I think it's RA.
R1A?
Yeah. RA, and this one is RB. Okay. So the Hamiltonian operator for this has several terms.
Yeah.
Okay? Let me write out the Hamiltonian operator. So the Hamiltonian operator in atomic units. Almost running out of space. Now you'll notice that it's missing all those constants, like the h bar and all that stuff. The reason why it's missing all those constants is because when you work in so-called atomic units, all of our constants and everything disappear. That's because, do you really think the electron cares about Planck's constant? Nope. Electron doesn't care about Planck's constant. Do you think the electron cares about what a kilogram is? No. Or what a coulomb is? Like all these things that we...
Electron has mass in kilograms, though. It's small.
But a kilogram is arbitrary. We have defined a mass called a kilogram.
Sure.
So electrons don't really care about our units. they only care about,
Why do we care about the feelings of the electron?
well, because when we only care about the feelings of the electron, we just get this simple Hamiltonian. That's why. Okay, so all of the constants associated with R units go away, and what you're left with is just the functional dependencies of what's there. So this is the kinetic energy term. It's del squared. It's an upside down delta, del squared. This is what we had as the second derivative with respect to x. You guys remember that in the Hamiltonian operator?
Is this del with respect to x, y, and z?
Yeah. So this is a three-dimensional problem, and so we have a new term. It's del squared. Don't worry too much. We're not going to do anything with it. This term right here, these two terms, are potential energy terms.
Just those two?
Or sorry, the electron. There's only one. So this is the potential energy term of the electron with respect to proton A. This is the potential energy term of the proton with respect to of the electron with respect to proton B. Okay, so this is all these things right here are all terms for the electron's motion. But we also have two protons. So, and they're separated by a distance r. This is the potential energy of the protons. So how close are the protons, right? You bring them closer together, the potential energy goes up because they're positively charged, right? So like charges repel, so you have to push them together, okay? These two terms are the kinetic energy terms for the protons. All right, so this Hamiltonian operator, with a very simple approximation, is to assume that the protons stay fixed in space. They don't move. This is an excellent approximation. It's called the Born-Oppenheimer approximation. Why is it so good of an approximation? Let's remind ourselves what kinetic energy is. Amanda, what's the equation for kinetic energy?
1/2 mv squared.
That's right. So what happens to the speed when I have a big mass?
Assuming you have kinetic energy constant?
Yeah, kinetic energy is constant.
It goes down.
It goes down. The electron is 1,000 times less massive than a proton. So, compared to the proton, the electron is zipping around very quickly. The protons are 1,000 times more massive. They don't move that fast. That's why this is such a good approximation.
What was the approximation? They have a fixed motion?
Yeah, that the protons, that the nuclei don't move.
So why can't you do this for helium?
Helium just has one nucleus.
Could you do the same approximation for helium?
No, helium has an electron-electron repulsion term. That's the problem, and you can't get rid of that. You can't ignore that. Okay, so we're left with, after we get rid of those, we're left with kinetic energy of the electron, and 3 potential energy terms. This problem is actually solvable analytically, but we're not going to do that. It's not very useful. Instead, we're going to apply something called the variational method to this problem. Okay? The variational method is an approximation that says that the energy is equal to psi star h hat psi d tau over the integral of psi star psi d tau. Here we go.
So born, but you just throw an h bar in there?
This is not h bar.
H
That's the Hamiltonian operator.
H hat's what I got.
Okay, and this is the energy for the variational method. Okay. Now, the variational principle says that the energy that you calculate is always going to be greater than or equal to the real energy. Okay, so what we're getting is a lower limit on the energy. But that's not something of particular concern for us. Okay, this is an approximation. And it's an approximation because it's only an approximation if the wave function is not the exact solution. Let's take a look at this problem if we have a normalized wave function that's an exact solution to Schrödinger's equation. You guys ready? Do you know what to do?
Wait.
Sort of. If we want to look at this, to Schrödinger's equation, we have this. Right? This is Schrödinger's equation. So we can replace all of that right there.
You solve for E?
Then, E is a constant. What can you do with constants?
Pull it out.
Pull them out of the integral. So you get this.
Then E is equal to E.
And E is equal to E.
Assuming you have the same bounds on the integrals.
Yes, the same bounds on the integrals. So if it's an exact solution, then E is equal to E. But we're going to work with approximate solutions. And this is our approximation, or our guess, okay? Our starting guess for this is that the wave function is a linear combination of a 1s orbital on proton A plus a 1s orbital on proton B. Okay? And you're like, wait, this is not antisymmetric. Are you thinking that? No? You're not, are you thinking at all?
What's the whole point of like...
So this is just a one electron problem. So there is no electron to swap it with.
What's the whole point of wanting symmetry or anti-symmetry in the first place?
It's a consequence of the fact that electrons are fermions and they obey Fermi-Dirac statistics. Fermi-Dirac statistics says that the wave function must be antisymmetric upon exchange of any two fermions. It's as far into the weeds as we want to get. Might not be satisfying, but you're welcome to do whatever reading you want to do outside of class.
I tried. I failed.
Okay, so this is our wave function. Okay, so in order to solve this integral, solve this problem, we have to deal with the numerator and the denominator. Let's deal with the denominator first. Okay, so the denominator is just this stuff right here. There's no Hamiltonian operator. Oh, that's so much easier. Let's do that.
No, we got rid of the Hamiltonian operator.
No, we didn't. I was just showing you that if the wave function is an exact solution, then you just E equals E. This is not an exact solution.
Okay.
It's an approximation. So the denominator looks like this.
Is this subscript A and B correspond to alpha and beta, or is that?
No, this is proton A and proton B. They are 1s functions on different nuclei.
So why are we doing A and B instead of like the parentheses 1 and 2?
Because we only have one electron.
Oh, this is protons instead of electrons. Okay.
Yeah, this is a 1s orbital on proton A and a 1s orbital on proton B. All right, so when you see a problem like this, what do you want to do? Let's foil it. Right, you distribute everything?
Does the star really do anything?
Yeah, watch.
Okay.
See, there it is. So I'm just doing first, outer, inner, last. That's foiling or distributing. How many integrals do we need to solve?
4.
4 integrals. All right. What does the first integral give us?
You can't take it.
It's 1 because it's normalized.
We know it's normalized.
How do we know it's normalized? Because we're going to work with normalized wave functions.
So we're just taking you for your word.
Weird. You can use an unnormalized one if you want. Oh, excuse me. I chose to use a normalized 1s wave function. What did you choose? What are you using, Aiden?
Follows your lead.
You're using a normalized one? Yeah. Why? Because that integral is 1. Okay, what about this one? What about that integral?
Probably 1.
It is not 1.
How would you think that?
I know. Why would you think that's 1?
I don't know, because I don't understand quantum and I'm taking your word for it.
Obviously, it's not 1.
Guys, just look at the problem.
Here, let me sketch out these wave functions. Right, we've got
How you sketch them out? Okay.
this is A, this is B. Okay, we're just sketching out what this looks like. This one looks like that. Looks like that. Okay. So notice I'm taking the product of these wave functions. Okay. So this is wave function A, this is wave function B, okay? And I take the product of the two. All right? So that means I'm multiplying them together.
And you're taking the area under the curve.
And we're taking the area under the curve. Okay? So when I multiply them together, I get, I don't know, something that looks kind of like this. When you multiply them together, I'm just going to look something like that, right? Way over here, this one is 0, so it didn't really, that one's 0. Over here, that one turns to 0. So anyway, it gives you this kind of thing right here. This is a measure of the overlap of the two wave functions. okay? Because we're multiplying the two together and then we're integrating. So this second integral right here is what's called the overlap integral. We're going to give that the letter S for the overlap integral, because S goes with overlap.
Yeah, that's exactly what it stands for.
I know, right? Okay. What about this next one? What is that?
That's probably.
It is another overlap integral. Yes.
Oh, I thought it was 1.
What about the last one?
That one's 1.
That one is 1. Because it's just 1SB, 1SB, right?
So why are we just writing capital S? Just because
That's what PCHEM textbooks use for some reason. I don't know. It's the overlap interval.
Thanks, Aiden.
Okay. We have like 5 more minutes. Okay. That's the denominator.
Are we going over the numerator tomorrow, or?
No, now we're going to do the numerator.
No. Got time?
No. No, we don't have time. Yeah, we don't have time. Yeah, we'll just call it. We'll call it truce. But it's about to get interesting. It wasn't interesting before? Well, it gets weird.
It's gotten weird since we started quantum. As soon as you start saying that momentum and position can't be observed at the same time.
All right, Zion. Hey, good luck, buddy. Let's. We're looking for what time are we looking for out of him? He's running. This is a 10K, I think, right? So, what do you think? Like 30 minutes? 30, 31?
Over under 30.
30? Yeah, 30 minutes. 30 minutes. You heard it here first.